So, good morning. I would like to welcome everyone to this webinar on nickel carbon footprint, new data, studies, and activities. Before we start with this webinar, a few technical items that I would like to mention. First of all, there should be interpretation available in Indonesia Bahasa as well as in English. I think we are currently facing a little technical problem. Claude is trying to sort it out, but there should be a little globe that you can where you can push the button, and then you should be able to choose the language. The second item I would like to mention is that we are going to have everyone being on mute. If you have questions, we would like to ask you to forward these questions in the Q&A. And what we will do is that together with the speakers, we are going to identify the most relevant questions. We only have a limited time, which is usually not sufficient to answer all the questions. So the most relevant questions will be discussed and answered at the end of all presentations. And I can promise that we are going to note down all the questions, and there will be a follow-up report that will be published after the meeting where all the questions that we received through the Q&A will be answered. And yeah, that's it. As we have a very busy agenda, I would like to directly dive into the introduction. So first of all, you are muted. The raise hand function is not working. And we are going to record the session. That's the most important point. As said, we are going to make a meeting report available, but also the recording as such, knowing that there's usually also a great interest in these webinars from North America, from people that might also not be available from Jakarta or Indonesia to attend. Antitrust, the Nickel Institute does not present forecasts or comments on nickel market prices, supply, demand. We are committed to full compliance with the competition or antitrust laws in all jurisdictions, and you will find further information on our guidelines on our website. About the Nickel Institute, I will keep this brief. We are the Global Association of Primary Nickel Producers. We are working in 4 areas, that is science, public policy and sustainability, market development and communications, and we have offices around the globe. I will show that in a minute. What we do is that we advocate for the responsible supply and sustainable development of nickel and the nickel industry. And you can see that we have a strong focus on science, public policy. We are looking into threats and opportunities, and we, with our communication colleagues, make the invisible metal nickel more visible. Our offices are distributed around the globe. So we have traditionally an office in Canada, our colleagues in the US dealing with science and shared services. Myself, Claude, and Pablo, we are working in the Brussels office. We also have an office in China, in Singapore, and in Japan. Now, coming to this webinar and why we are organizing these webinars, I've taken here figures from the International Nickel Study Group from their yearbook that was published in end of 2024. You can see here figures until 2023. The light greenish bluish bar in the middle is actually Indonesian nickel mine production. And what we can see is that since 2014, the mine production in Indonesia significantly increased. And what we heard is that in 2024, more than 60% of all nickel mined globally is coming from Indonesia. And the other point, and Tom is going to talk about this, is that linked to the nickel production, we also have cobalt as a byproduct. And in the meantime, Indonesia is also the second largest economy globally that is producing cobalt. Why are we organizing these topical webinars together with the Cobalt Institute? we see that there are increasing sustainability requirements, which are formulated by markets, by regulators, by investors. And these requirements can potentially affect the access to markets for Indonesian nickel producers, license to operate, but also access to capital. When we talk about, for example, the financial community looking into sustainability requirements. And therefore, we agreed with our colleagues from the Cobalt Institute to organize these topical webinars to inform what needs to be done by Indonesian stakeholders and how our both institutions, Cobalt Institute and the Nickel Institute, can support companies, but also the government in achieving their targets. This topical webinar, we shared with you a program that is here seen on the slide on the right side. The major aim is to provide an overview on the developments in measuring the carbon footprint of different nickel products, to inform on decarbonisation activities undertaken or investigated by the World Resources Institute Indonesia, as well as the Cobalt Institute. And overall, I think it's also about showing the relevance, the urgency, and the business impact that the carbon footprint calculation might have. The speakers, and then I will end with this today, are on the one side, Pablo, our LCA and sustainability specialist here at the Nickel Institute. He will introduce us into the update of the Nickel Institute lifecycle data. We have Rohin from Minviro, who's going to talk about a study that Minviro has done for the INSG, looking into carbon emissions from nickel mining, refining, and recycling. Edi is going to provide us with an insight into the work done by the World Resources Institute Indonesia on a decarbonisation roadmap that is under development for the nickel industry in Indonesia. Tom presents some work done by the Cobalt Institute on a cobalt decarbonisation pathway, and I will say a few words about a recent discussion that we see popping up around low carbon nickel and our views on whether this is a meaningful debate or not. So with this, I would like to ask our first presenter, which is Pablo, to take over the control and to actually present the work that we have done related to the update of the nickel lifecycle data. Pablo.
Yes, thank you so much, Mark, for the introduction. I'm now sharing the slides. Can you see them properly?
We cannot see your screen, Pablo.
Okay, let me try again. What about now?
Yes.
Yep, perfect. Thank you. So I'll give it a start, and thanks for the introduction once again. What I want to present today to you is the work that we as Nickel Institute have completed in 2024. And the work is focused on updating the life cycle data for the nickel products that are produced by our member companies. And so I will show you what the key findings of this study are and what the way forward is. So first, to start, just to recall a bit the scope of the project, we are here conducting a cradle-to-gate life cycle assessment of the most relevant nickel products that our members produce. And we have a reference year of 2021. This is an update from a previous exercise. Our latest one was done based on data from 2017. And our life cycle assessments are always based on hard data from member companies. The products that are in scope are class 1 nickel, so a very high purity nickel metal. We have also ferronickel, an iron nickel alloy that is used on the stainless steel industry. And then finally, the nickel sulfate hexahydrate, a nickel chemical that is also important in several supply chains. We commissioned this work with Sierra, which is running the updates for us for already quite some time. And also quite importantly, once the calculations are done and the report is written, we also conduct a critical ISO review to make sure that the report is in conformity with the requirements under the ISO standards. And this was done by a panel of 3 independent experts, which provided into their review their different expertises, both from the LCA, from the ISO side, but also from the industry. So yes, in terms of system boundaries, as I said, this is a cradle-to-gate study. So we are going to include impacts associated to the extraction of resources from nature, but also all of the processing to the point at which the refined product leaves the factory gate. We consider this is an appropriate choice of system boundaries also because there are nickel products are serving as intermediates for many different product life cycles. And major process steps that we are considering here are the mining, the beneficiation or the ore preparation in case of lateritic ores. And then we have primary extraction, which covers both pyrometallurgical and hydrometallurgical processes. And we also cover refining. Next to that, we have also the transport of the ores and the concentrates and the mats, and the auxiliary and ancillary materials that are used on site, the tailings and the waste treatment on site that are also part of the boundaries. Of course, not all this process will apply to every manufacturer or to every processing route. So for instance, ferronickel producers won't have a refining stage, but this is what overall the study is focusing on. When it comes to the sites involved, this slide is showing you an overview of the list of sites and divisions involved in the project, as well as their location, the nickel products that are relevant for them, and the types of ore and mine. So you can see that the study is actually considering both surface and underground mining or of both sulfidic and lateritic ores. And it also includes pyro and hydrometallurgical processing routes. In terms of geographical coverage, we have also presence in all continents, North and South America, South Africa, Australia, some parts of Asia, and also Europe. Yes, when it comes to market coverage and representativeness, you can see on this slide what's the share of nickel members production that is represented in the study. It's nearly or 100% or nearly 100% for all products. When it comes to the share of the global production that is being represented, this is not as high. It's around 50% for nickel, 35% for ferronickel, and less than 8% for nickel sulfate. So when it comes to representativeness of global production, here we cannot really consider the results as highly representative, as they are well below 80% of market coverage for all products. And there are also significant players in certain geographies that are not well represented and that account for a high share of the global markets. So here you see the average results for the global warming potential and the other impact categories that we focus on our study. For the purpose of this webinar, I will mostly talk about global warming potential. And you can see that we have for nickel class 1 a value of roughly 13 kilograms of CO2 equivalent per kilogram of nickel. For ferronickel, we have a value of 51 kilograms of CO2 equivalent per kilogram of nickel in ferronickel. And this is assuming a 27% content as an average of nickel in ferronickel. And the value for nickel sulfate is around 3.5 kilograms of CO2 equivalents per kilogram of nickel sulfate hexahydrate. Now, if we go into a bit more detail on the global warming potential and looking into the impacts for class 1 nickel, we can see that around 60% of the total global warming potential impacts are caused by direct activities and electricity supply. And then almost 18% is caused by the raw materials and the sulfur, which itself accounts already for about 7% of the impact. So this is quite an interesting thing to see. When we go into ferronickel, we can see there that almost the totality of the global warming potential is caused by direct emissions, fuel production, and electricity supply. For direct emissions, it's about 61% of the impact. For fuel production is 12%, and for electricity supply is 22%. It's something important to highlight here is that this assessment is only valid for this main study, and it might change, for instance, if other production technologies and geographies are considered. Important is that the study does not include any nickel pig iron production, particularly no production also in China. And so, yeah, since no MPI facilities are represented, the values are only relevant for ferronickel. And for nickel sulfate, we can see that around half of the impact is caused by the direct activities, so the emissions on site, and also the electricity supply. A value of 16% is caused by auxiliaries. This is due to materials such as sodium hydroxide or sulfuric acid that are being used in the process. And we can see also that 25% of the impact is caused by the purchased raw materials, which go into the nickel sulfate refining process. In this next slides, I'm going to show you a further insight into the impacts, which are going to be broken down into process steps and also into scope 1, 2, and 3 emissions according to the GHG protocol. For class 1 nickel, we can see here that primary extraction is the main contributing process step with around 53% of the impact. Most of the emissions are direct emissions on site, so scope 1. And we can see also that the external purchased concentrate that is then processed contributes around 18%, which is showing up also under scope 3. Refining contributes 12% to the impact, and mining and beneficiation or ore preparation contribute also with similar shares between 7 and 8% to their overall impact. And in this slide, we can see a more detailed analysis. We can see that power generation and direct on-site emissions are accounting for the major shares of the impacts in most of the process steps. And as said before, the impacts from the purchased concentrate are also important. Now, moving into ferronickel, we can see that primary extraction is also the main contributing step with 81% of the impact. Beneficiation and ore preparation would be the second largest contributor with about 15%. And we can also see that most of the emissions would be classified as on-site emissions, so scope 1 emissions. In the next slide, we can see again a more detailed analysis. The major contributors during primary extraction would be electricity, reductants and fuels, and also the resulting direct emissions. In the beneficiation and ore preparation stage, the impacts would be mainly due to the direct emissions and also the fuels used in the drying process. Moving on to nickel sulfate, once again, primary extraction is the main contributing process step. And one of the main impacting factors here is the lateritic route. We can see that the raw material from third parties contributes with about 25%, and this includes lateritic intermediates as well as different sources, including class 1 nickel powder that is then refined, or other nickel-containing intermediates that are converted into nickel sulfate. Most emissions in this case, as opposed to the other products, are classified as scope 3. And here we can see a more detailed analysis with the major impacts from scope 1 emissions being due to direct emissions from primary metallurgical extraction. This is mainly due to the use of reductants as well as the necessary steam and thermal energy that is used and produced on site. The sources of the scope 3 emissions are mainly the external purchased raw materials, and also the auxiliaries used in primary metallurgical extraction and in the refining process. The refining itself has similar shares of contribution from auxiliaries, electricity, and direct emissions. And the auxiliaries mainly contributing to the refining process are sulfuric acid and sodium hydroxide. Now, I want to explain something else that we have done after finalizing the calculations, which is the fact that we have a varying membership, and so we can't always directly compare our results to the previous exercise we did, in this case, the one we did in 2017. So in order to allow us to compare and to derive some trends and to make some conclusions, we conducted a sort of a normalization of results to ensure that we can better analyze the underlying differences between the data sets. And the approach that we followed is we updated the background databases used in both studies to make sure they were the same. So the 2017 study was recalculated according to the new database. We also excluded from the previous study the companies that would not participate in the last one, to ensure that also the population we were analyzing and averaging was the same, and to be able to show the normalized results. Next to that, we also conducted an evaluation of the changes in production volumes per company, and also any changes in the foreground data to identify the main influencing parameters to the impact and provide more detailed insights to our members. And here, yeah, we can see that the normalized results, so the comparison between the latest life cycle data in 2021 and the data from 2017 already corrected. We can see that it's showing similar impacts both for ferronickel and for class 1 nickel, while for nickel sulfate, we observe a 35% reduction of the impacts. Now, when we look into the reasons for these differences, or for being in the same order of magnitude in the case of ferronickel and class 1 nickel, this is a combination of changes due to, on the one side, increased energy efficiency, but also a decrease of nickel content in the ores, and then having, in some cases, more granular data, which allows us to do a more accurate allocation, even like process-specific allocations, where before that was not possible. And then the fact that we've also considered supplier-specific power supply information whenever that was available. And also the latest study includes more renewable energy sources. So these are things that are causing the difference, or that are balancing out and causing the volumes, the results to be within the same order of magnitude. We have also observed that some power grids have less grid losses, which is beneficial in the results. And when it comes to the share of lateritic versus sulfidic production, we observe a very similar share as we had in our previous study. What we did observe, nevertheless, is that the production volumes for most of our members have decreased, and this is also affecting the result to a certain extent. So just to finalize and to conclude, I want to conclude that the study uses overall better quality of data, but also a lower geographical representativeness. And this is particularly important for ferronickel and nickel sulfate. And this is mostly due to increased production outside of our membership. As a next step, what we're trying to do next is to extend the scope of our LCA from a Nickel Institute average to a global industry average. And the intention would be to collaborate with stakeholders in order to fill the data gaps and cover the remaining market, particularly for nickel metal and nickel sulfate. The final aim would be to derive the global average data that we can introduce into relevant databases for use under different initiatives, being regulatory requirements or conducting LCAs for certain downstream products, etc. And in addition to this work, we are also preparing for our next update of life cycle data, which will be started in 2026, next year. So we are preparing everything so we can start it over and have this based on 2025 data as reference here. And that's the end of my presentation. Thanks so much for your attention, and I'll give the floor back to Mark.
Yeah, thank you very much, Pablo, and thank you very much for staying within the time frame that we set. With this being said, I would like to directly hand over to our next speaker. Now, let me check once again the program. Our next speaker is going to be Rohin. Yeah, thank you, Rohin, who's going to talk about the study that Minviro undertook for the International Nickel Study Group. So, Rohin, the floor is yours.
Thank you. Thank you, Mark. Hello, everyone. My name is Rohin. And yeah, this afternoon for some of you, I would like to talk about a study that the INSG commissioned from us at Minviro a couple of years ago now, entitled An Assessment of Carbon Emissions from Nickel Mining, Smelting, Refining and Recycling. And actually, given everything that Pablo has just mentioned, I think this will be a really complementary set of data for those of you in the audience. I've seen some of the questions, and maybe some of the questions I can support answering with some of the work that we've done here. And Mark had given kind of the general prompt around the global picture for different nickel products and like carbon trends and hotspots. So I'm definitely going to try and focus on those parts of this study. I thought I should do a brief introduction to Minviro and myself. So yeah, my name is Rohin. I'm a mining engineer by training and by background, but I have been working at Minviro now for 3 years, working on life cycle assessments of mining projects, but also lots of systems and products within the energy transition, from things like batteries, but also photovoltaics, and very recently, lots of hydrometallurgy for recycling of metals. Minviro is an independent startup where we have a vision and mission to ensure that we can make things with minimal effects on the environment, and we would like to guide that development with scientific knowledge. And this is what we have tried to develop all our reporting and our business on. We have 3 parts of our business, and they're all quite interlinked. So there are 2 parts that are much more closely tied to the business. That's the consultancy team and the research and development arm. And this report for the INSG was commissioned and done by the consultancy team. And we have worked with a number of people, products, systems to help them understand their environmental impact. The R&D team support with that. They also get to work on more blue sky thinking and research grants that can influence and support with some of our consultancy work. We also have a software team. I will talk about that a bit more in a moment. But yeah, I work now as a product manager in the software team trying to make LCA software. Now, I know that Pablo has just spoken lots about LCA, but I thought it might be worth going over LCA as a methodology and why we use it, and the real strengths of the methodology, as well as perhaps the weaknesses. I'm an engineer, so I am a fan of diagrams, and diagram on the right of this slide is a really simple but I think powerful way of showing why LCA is so powerful. I saw that someone in the chat had asked about what things were considered in or as part of scope 3, and I think this is a good way of partially answering those questions. I know the system the Nickel Institute have done is not going to be exactly the same as all the ones that I'm about to show, but in principle, all the inputs required to make a product should be considered as part of an LCA, as well as the outputs. So a good example might be for let's say you're doing HPAL for nickel lat, and you need limestone to neutralize the acid at the end. You would consider the impact of mining the limestone as well as the emissions from the neutralization reaction at the end. Those would all be taken into account as part of the carbon footprint of the nickel product. I think it's worth iterating as well, as Pablo highlighted, that LCA can cover more than just CO2. Today we're focusing on CO2, but the Nickel Institute study has a couple of other impact categories that are really interesting. And obviously, I think we're biased at Minviro, but we're backed up by Pablo and some other credible industry that LCA is the best way to quantifiably source materials for the energy transition and understand their impact. So I briefly mentioned, and I'd be remiss to not mention that at Minviro we're developing software for LCA experts to do the best LCAs they can, and as part of this, lots of the nickel data I'm about to show you can be accessed through our software tool. So please do get in touch if you're interested in learning more about how you might be able to do your own LCAs, or how you might be able to gain access to some LCA data on nickel carbon footprints. So in the theme of doing an LCA, I wanted to start with the goal and scope. Actually, I'll start with the diagram on the right, because that, again, really clearly indicates kind of what we did as part of this study and what I'm about to describe in the following slides. So a really core part of what the INSG wanted to understand was main sources of GHG emissions in the whole nickel value chain. So we wanted it to try and be as representative as possible of technologies around the world. And so that means that we had to try and cover the main core nickel products. And we did it in kind of a modular basis, similar to what Pablo was just saying, where we have calculated individual gate-to-gate studies or cradle-to-gate for nickel mining, but we kind of undertook gate-to-gate studies of each product. So you can look at the climate change impact, for example, of just nickel matte from a flash smelting process in nickel sulfide, or just nickel laterite ore mining. And so in the following slides, you'll see kind of gate-to-gate results of each product. And that was hopefully going to, in the end, provide evidence-based, informed development decisions for nickel refiners, smelters, miners. So a quick disclaimer that this is not intended to reflect any specific producers. We did this on a technological basis, so we're trying to represent technologies and not specific companies or specific regions. This is also based on publicly available data and therefore don't represent a specific company. And this is done for the reference year 2022 to 2023. And inherently, LCA has some uncertainty. So please do not consider this having the same precision as any financial accounting. So onto the results, or onto some results, I should say. In the following slides, you'll see lots of graphs like this, and effectively, similarly to Pablo, on the y-axis, we're always going to have kilograms of CO2 equivalent per nickel contained. So that allows us to make comparisons between different products. For example, in this instance, we have kilograms of CO2 equivalent per kilogram of nickel in ore as opposed to per kilogram of nickel ore. And also, as part of trying to be as representative as possible, we try to model a low CO2 case and a high CO2 case so that a range of values could be interpreted and you could understand what maybe the best case and the worst case might be. Obviously, we've not got an exhaustive list of things, so it's not going to be the absolute minimum and the maximum, but we try to make it as representative as possible. And yeah, I think going on to some interpretation, initially, I think the thing that sticks out the most to me is the massive variance in CO2 impact of sulfide or mining. And this is a good example of talking about some of the modeling that we did at Enviro. So here, not only did we vary the energy source for underground mining, but we also varied resource grade quite heavily. And actually, in this instance, resource grade is really the defining characteristic in the variation in CO2 impact. The lowest grade ore we modeled underground was about 0.8%. And if you think about it, taking out 1 ton of 0.8% grade versus a ton of 4.2% grade, you have to do much more work to get the same kilogram of nickel out from the low grade versus the high grade, which really explains a large part of the discrepancy in the CO2 impact here. And then in stark contrast, both the open pit methods have much lower CO2 impact, but again, resource grade is the big driver in the change in CO2 impacts between the high case and the low case. We also modeled some energy like electricity grid mix changes between the low and the high grade, but really the thing that was driving this was resource grade. And on concentrating sulfidic ores, electricity again is, electricity is the driving factor here. Grinding and flotation both require some electricity, grinding obviously more than flotation. And yeah, a low CO2 grid mix is going to be one that has a much lower CO2 impact. So I know that Mark asked to speak a bit more about where things are going in Indonesia, and I think that the big story, as the production figures showed by Mark earlier, is how much nickel production has surged in Indonesia and how many reserves. In my crude map, you can see that there still are, and I think tied to that inherently is like smelting technology and smelting production improvements or increases. And twinned with nickel, we have to talk about, I think also, if we're talking about nickel climate change impacts, we have to talk about coal mining, where since 2022, Indonesia has become one of the 3rd largest coal producers. And that is going to be reflected in my MPI figures that you'll see in a moment. So I would like to note that this is meant to be representative of HPAL across the world and RKF across the world. However, I think RKF is dominated by production in Indonesia, but the HPAL numbers here do reflect places like Madagascar, New Caledonia, as well as Indonesia. So on the climate change impact from producing MPI via RKEF, I think the thing that stands out is kind of this high baseline number, that there is a strong reduction that we modeled that is possible. However, inherently there is a requirement as in a furnace for a reductant, and not almost always that is fossil fuel based, which means that there is not such a big delta in the high and the low case here. The other driving factors are just requirements for heat, and if that's provided by a fossil fuel, then that can really increase the climate change impact. But you can reduce it equally by using electricity to source some of that heat, and if you use a low carbon electricity, then you can reduce that further. On the HPAL side, there's a bigger delta between the high and the low case that we modeled, and some of that is due to using sulfur to generate heat as opposed to a carbon source. But also, if you can source, again, low carbon electricity for the process, that can really influence it. And we also modeled some scenarios where some of the ore put through the process has carbonate bearing minerals in it, where they do some of the neutralization before requiring any limestone or additional limestone, which can further reduce the CO2 impacts. I also didn't want to leave out smelting and refining. There are similar trends across here, but I will quickly touch on things that are not in the trend. And that, for me, initially on the left, is the change in electric furnace smelting. This has a baseline level of emissions from carbon-containing reductants, but also is sensitive to grid mix because it's an electric furnace. So if you model the furnace with a low CO2 mix, then you can really have some strong reductions, but also equally a high CO2 impact. And then flash melting and making matte from MPI have a big delta, but mainly from grid sensitivity or electricity requirement sensitivity. I think in flash melting, depending on how you model, like how heat is used and how we model heat, that can really drive the impact up. So using something like heavy fuel oil versus natural gas can really drive sensitivity. But yeah, I think grid mix is a real, or electricity impact is the real driving factor between the low and high scenarios here. On the right, talking about making class 1, carbon refining is really interesting, where inherently, again, you can't decarbonize it too much, as you need a source of cracked gas that is almost always from natural gas. So you can reduce the impact by reducing maybe some of the climate change intensity of the electricity required, but there is going to be a baseline level of CO2 emitted from the process, where electro-refining is almost completely driven by the climate change impact of the grid mix that you use. Finally, I wanted to touch on crystallization or making nickel sulfate, because that's one of the driving factors in making batteries for the energy transition. And so again, here that there is a baseline level of impact from both processes, which is turning MHP and matte into sulfate. And for example, we still have a baseline level of impact from things like sodium hydroxide, which are required to ensure that we have the right pH in the process. But mainly the impact is driven by heat required, as well as electricity, heat for crystallization and electricity for the processing. And if that heat is coming from a fossil fuel, then that increases the impact. So yeah, I think the real common trends that we identified in this report are quite evident and highlighted actually on this end slide, where there is some inherent decarbonization that is possible, but some that isn't, because of the way that like maybe reductants are required, or there is going to be a baseline level of chemical impact. But inherently, grid mix or electricity supplied to processes is a real driving factor, as well as heat. And I kind of concluded that just here, that the sensitivity of the nickel value chain is to heat and electricity. I also wanted to highlight that I think, yeah, we learned a lot about how modular LCA can be, where you can tie bits together doing this, and how interesting interpretation can be on both a system level, but also like a modular part of the system. And we also had some work on this on recycling that I didn't include in this because I didn't think it was so relevant, but recycling of NMC batteries is going to be really significant in reducing CO2 impact of nickel, but not for a while. Those batteries are not going to be at the end of life in a meaningful way for 8 to 10 years. So that's an interesting dynamic. But if you want to read more, then you can do in the report. And there's a lot of granular data in the report that I didn't get to touch on in this today. So yeah, you can find that report through the INSG online, and you can access some of this data through our software cycle. Thanks.
Yeah, thanks, Rowan, and thanks for staying in the time. I know it's a challenge when you have to summarize such a wonderful report as the one that you have done for the International Nickel Study Group. Maybe just to explain, as I think it is worthwhile to also explain to this audience, the International Nickel Study Group is a governmental organization of different economies that have an interest in the metal nickel and in statistical information. So it's a great source of information when it comes to statistics that we use often enough in our daily work. So thanks, Rowan. And I already saw there are a number of questions related to the presentation of Pablo and Rowan. I answered many of those. So Pablo, Rowan, you can already prepare yourself by looking into the Q&A section and see what I responded. We will pick up some of the questions later on. Good, then I would like to hand over to Egy. Egy Suaga from the World Resources Institute, Indonesia, where he's working as a climate manager. And Egy is going to share with us the work that is currently undertaken by WRI Indonesia on drafting a decarbonization roadmap for the Indonesian nickel industry. So, Egy, the floor is yours.
Yeah, thank you, Mark, and thank you for having us here. Yeah, can you see my screen now? Okay. So yeah, good morning, good afternoon, everyone. So I would like to explain or present our ongoing work about the Indonesian nickel decarbonization roadmap. So actually, this is our collaborations between WRI Indonesia and the Ministry of National Development Planning, and hopefully the report will be launched in the next coming weeks. Just to give you a background, that as Mark mentions in the earlier, that Indonesia nickel productions has been increased. So we see that since 2013 until within the 10 years of period, so we have like twice increase of the nickel productions in Indonesia, and it creates a significant impact to the economy, but on the other side, it creates cost in the form of the emissions coming from the mining and processing. So this is actually become the challenge for Indonesia, because Indonesia has also have a commitment to reduce the emissions based on the climate target through the NDC, and also Indonesia has also put some emission reduction target in the national long-term development planning, and also we have like long-term strategy on low carbon and climate resilience to achieve net zero by 2060 or sooner. And based on that, we identify how Indonesia can, like move toward a low carbon nickel productions. So we start the study, I think, a year ago, and started by identifying the hotspots of the emissions from the end-to-end processings in nickel. We identify at least 4 stages, 4 big stages in this nickel processing, from mining, extractions, refining, and product manufacturing. But we actually we put some like barriers or the boundaries of our works on only focusing on mining, primary extractions, and refining, because these 3 stages are the largest emission sources from the nickel processing. So as you can see, the primary extraction count around 90% of the emissions, while the refining contribute around 8%, and the rest are from end product manufacturing and mining energy use. This is also to give you a picture. So we use the GHG protocol to calculate the emissions coming from nickel industries in Indonesia. So we gathered data from 20 nickel companies in Indonesia and develop kind of like an average of emissions that are coming from these nickel industries. The largest contributors are coming from the pyrometallurgy smelters. It takes around 98% of the emissions from 170 million ton CO2 emissions. If we compare to the national emissions, so it's accounts around 22% of the national emissions in 2023. The rest is coming from the hydrometallurgy and the mining. So the nickel intensity of Indonesia is considered really, really high. And this is also because of the type of the ore of the Indonesian nickel, which is mostly our laterite ore. And yeah, we identify that the dominations of the emissions are still coming from the electricity generation. So the significant increase of the captive coal power plant contributes significantly into the emissions from this nickel processing. As you can see that from 2017 until 2023, the additional of the captive coal is around 7.9 gigawatt. So you can see the rest of the technology of the renewables are really, really low compared to this coal power plant. And if we combine the pyrometallurgy and the HPAL in terms of the electricity generations, it counts mostly like 100 terawatt hour, and it's quite similar with the selling of the PLN to the household at national level. So it's really, really huge in terms of the energy use for the nickel productions. And our research divided the regions into the 3 clusters. So we divided this is based on the characteristics of the geographical and also with the location. So we divided, there are 3 clusters that we are working on. First is on the Central Sulawesi, second is on North Maluku, and the third one is the Southeast Sulawesi, South and Southeast Sulawesi. So this is I think the data is on 2023. So we identify around more than 50 companies, smelters and mining on the nickel within these 3 areas. And again, the most of the emissions are coming from the pyrometallurgy. You can see the divisions of the emission sources coming from the coal, diesel, electricity. So yeah, this is just to give you a highlight and map where are the emissions coming from this area. And this is to show you our projections. So basically, because Indonesia has a target to reduce emissions, and also the long-term national development planning are within the time frame until 2045. So our works is also try to align with this national targets, and based on this and based on our analysis, the emissions will keep increase because there are several pipeline of the companies since 2027 and until 2030. So there are several pyrometallurgy and hydrometallurgy companies are already in the pipeline. So if we are, let's say, continue the trajectory, there will be more than 149 million ton CO2 emissions increased from the current state and status of level of emissions. Some of the emissions are coming from the because of the declining ore grades, which in our research it creates the processing needs more energy intensive. So the emissions are increased because of the ore grade declining in the next future. Now, how the decarbonization framework and how much actual resources potential in Indonesia based on the three cluster of the locations. So first, we developed several strategy. So there is no silver bullet to reduce emissions in the very complex and huge emission sources. So there are at least 4 strategy for the abatement and 1 on the removal. But again, our works is mainly focusing on the abatement. So we put aside for the removal as for now. For the abatement, so there are several strategies started from the energy and material efficiency, fuel switching, material substitutions, and also the how we can develop the low carbon electricity and electrifications from the energy sources. These 4 main pillars or building blocks to abate the emissions coming from the nickel mining and processing. And this is just to give you a highlight. So we developed 2 scenarios. We developed the moderate scenarios based on the current infrastructure, but we also identify several potential or increase the in infrastructure that can support the government in reducing emissions in the 3 clusters. So we exercise this based on these 4 building blocks from the energy efficiency, fuel switching, material substitutions, and also low carbon electricity. If you can see the difference will be in terms of the number, but on the cluster 2 in North Maluku, if we see this is the for the ambitious scenario, we will need to put the hydrogen power plant because I'll tell you later because why we have to move with the hydrogen power plant for the North Maluku cluster. So yeah, this is to show you. So we identify the potential renewable energy because the biggest contributors of the emissions are coming from the electricity generations. We identify the potential of the at least 3 renewable energy sources on the solar, wind, and hydro. So and we overlay this potential with the feasible land use area that can be used for this 3 technology. So we remove the forest area, the flooded vegetations, the cropland. So we exclude that area. So we only put like built area, backgrounds, shrubs. So potential area that can be used for the electricity generations using these renewables. And you can see that this is quite vary. So for the solar, we have like around 200 gigawatt potential. Wind, we have 11. Hydro, we have 13 gigawatts, but the locations is quite scattered. So this has also become the challenge when we are talking about the energy sources, because mainly this potential energy, the locations are far from the mining and smelter locations. Yeah, and this is the scenarios that as I mentioned before, we developed the two scenarios, the ambitious and the moderate scenarios. So based on our calculations, we iterate several times on this. Yeah, for the ambitious scenario, we actually can hit the target of the national long-term development planning. But it seems that for the moderate scenario, we cannot achieve the target. So actually, the desirable scenario we use is the ambitious scenario to reduce emissions in these three clusters. This is the pathways. So you can see that we use the various combinations of the emissions reductions pathways from the energy sources, the processing, and in the beginning, the potential actions to reduce emissions are coming from the processings, because the biggest would be coming from the electricity generations. But again, the challenge is it's really challenging to shift the energy sources from captive coal power plant, the existing captive coal power plant, to renewables. And this is just to show you, because once we develop the scenario, we also have to identify how this scenario can be operated or can be implemented. So let's say for the optimistic scenario, because we have to use biomass, there will be 10 million tons of biomass needed to replace the reductant, the coal reductants. The problem is the locations of the biomass are mainly located in Sumatra, in Kalimantan. So there are lack of biomass sources in Sulawesi, in Maluku, that's are really needed for the reduction of the coal. The other thing is that we will need like 6 million tons of LNG, around 6 million tons of LNG, to displace coal usage in rotary dryers and kiln. Again, this is quite challenging because of the transportations, the connections, and also inadequate infrastructure in and pipe distributions in these locations. There will be around more than 700 million liters of biodiesel. Let's say if you would like to blend around 70% of the biofuel. Again, there are really lack of the infrastructure, but and also we need some mandatory blending rate to increase the biodiesel from the existing B40 to B70. And the last one is the renewable energy power plant should be integrated into the grid. So you can see it in the central Sulawesi, the technology can be covered by the solar and hydro. But in North Maluku, there is no hydro or wind potential there. So the options, if we would like to meet the target, is to include the hydrogen in the North Maluku area. So with that, we can cover the existing and the future, the upcoming energy sources target for these three areas. Again, the issue is like 45% of the renewable energy potential is located far away, more than 20 kilometers from the existing grids. So we need to add the new infrastructure to connect the existing grid to the renewable energy potentials, and to the grid to the smelters locations. Again, this would be, like challenges for the government, and also to will increase the investment cost of the transmissions. I think this is my final slide. So based on that, so there are several challenges that remain. First is because again, the infrastructure is still limited. So low carbon technology and material is very lacking in terms of the supply. So we need to increase this infrastructure. The other one is the cost is still high for decarbonizations. Because we will need the transportations, the technology will be needed for this decarbonizations processing. And the third one is we are still facing the unclear standard and monitoring systems. Actually, we are now step into the developing the standards for the ESGs in Indonesia. So hopefully we can continue our work from the emissions reductions to increase the standard of the ESG for the nickel processing in Indonesia. I think that's all from me. So I'll pass back to Mark. Thank you.
Yeah, thank you, Eggy. Also for staying within the 20 minutes. I'm very impressed that all the speakers so far did not exceed their speaking slot. That's very good, as we need time at the end to address all the questions that are right now coming in. And Eggy, it's also for you. You might want to have a look to the Q&A as there are a number of questions that came right now up related to your presentation. With this, I would like to hand over to Tom. I think it's going to be right now a very nice combination. So another decarbonization, in this case, a pathway that Tom is going to present from the cobalt perspective, coming more from the global scale, but then also zooming into Indonesia. So Tom, we are looking forward to hearing and listening to your presentation.
Thank you very much, Mark. Good morning, good afternoon, everyone. I've got a hard task to keep up with everyone else, keeping on time, but I'll try my best. So presenting today the Cobalt Institute's work, building on sort of work we've done in the past on life cycle assessment and so on. We did a decarbonisation pathway for the global cobalt value chain. Just here, by just, we mean just transition. And we take quite a broad view of what that means, and I'll round off this presentation with a bit of a description of our view on just transition. But before we start, I just want to introduce the Cobalt Institute for those who aren't familiar. So we're the global not-for-profit member-led industry association. We represent the whole cobalt value chain, so producers, end users like battery manufacturers, recyclers, traders, midstream as well. And we're here to promote the safe, sustainable and responsible production and use of cobalt in all its forms. So we're a bit of a knowledge centre, and I'll be sharing materials from a number of documents today that are available on the Cobalt Institute website. So please go there to access more details, and indeed the reports I'm showing today have a lot more detail than I have time to show. So please follow up there. I thought I'd start, and this is one report we actually published last week at our Cobalt Congress, our conference in Singapore. It was held in Singapore this year. We do an annual market report. This is for 2024. So I'm sharing some data from that. But just to give some context, and Mark up front mentioned cobalt obviously is predominantly a byproduct of either copper or nickel production. And here we have data from our market reports really showing how nickel has roughly tracked around a quarter of cobalt production. So the majority of cobalt obviously coming from copper cobalt routes such as the DRC, but nickel maintains its importance. And as the volumes coming out of the DRC have increased, Indonesian production has also increased. So whilst the rest of the world has stayed rather static as producer country, Indonesia has been producing increasing amounts of cobalt for the nickel cobalt route. And in 2024, that was some 12% of global mine supply. So that made Indonesia the second biggest producer, up from 8% in 2023. We're seeing over 80% year-on-year growth there. Now, this cobalt is mostly in the form of mixed hydroxide precipitate, mostly coming from the high-pressure acid leaching HPAL route. And perhaps one thing worth noting in the context of this conversation is that in our report, we have some data from Benchmark, who are our provider for this report, and they modelled theoretical routes for DRC cobalt and Indonesian cobalt, and we see that the HPAL from Indonesia potentially has a higher carbon footprint. So this is something we would like to see addressed. So onto the report itself, the just cobalt decarbonisation pathway. So here we looked at scenarios, and we built up potential scenarios for demand and then supply through to 2050. We projected what we assume industry emissions would be. Then we identified the abatement opportunities, and obviously there are CapEx and OpEx costs associated with these. And perhaps this is a good point to highlight. Obviously, as a byproduct, often we're talking about cobalt being as like a mixed ore with nickel or copper, and so we often need to use allocation to assign capex or carbon dioxide and so on. And generally, we use a mass allocation approach. But the report does also identify cobalt-specific abatement and capex and opex as well. But something detailed we don't have time for today. Framework conditions as well. We also identify the sort of policy conditions and what needs to happen to really help enable this decarbonisation. And then this just transition piece, again, that I will end this presentation on today. And just some highlights. So in 2023, we saw cobalt industry emissions being some 4.6 megatons CO2 equivalent. Again, something I won't touch on today, but is becoming increasingly relevant. Recycled cobalt, so secondary cobalt, we were projecting will meet 39% of global demand by 2050. This predominantly from end-of-life EV batteries. And then we have this capex of some $1.6 to $2.1 billion, which would be required to abate some 80% of emissions by 2050. So I'm going to run through how we sort of built up our scenarios and projections, and then I will touch on some case studies we had for different countries, but in this case I'll focus on Indonesia as well. Some interesting data we have there, and then finish up the reports. But firstly, we looked at historical demand. So from 2019 to 2023, and obviously there's been this huge growth in demand, particularly from batteries and specifically EV batteries, and so we've seen this 10% per annum growth in demand, and there's small growth as well from other uses such as high performance alloys, and then we modeled the supply over this period as well, and we see primary supply meeting over 90% of this, and recycled material, secondary material becoming increasingly important. And then we modeled some industry emissions, and I think the first thing to note is that scope 3 emissions predominate here. So imagine use of, say, chemicals in processing, auxiliaries, and so on. But we see a growth in emissions aligned with the growth in supply to meet this demand, some 58%. So that's getting us to our 4.6 megatons of CO2. And so from this, we built up our base case scenario, where we're seeing this continued growth in demand, again, driven predominantly by EV battery growth, but also we're seeing increased growth for other cobalt uses. So we know cobalt's used in alloys and catalysts, magnets, and so on. So defense and aerospace are becoming increasingly important, and this increases the demand. And so from there, we modeled the supply that would be needed to meet this demand. And on the left-hand side, we have our understanding of the existing projects and the projects in the pipeline, these blue bars. Then the increasing importance of secondary materials, so that's the brown bars. And then there's this additional supply needed. And here we've made the assumption this would be continued use of DRC and Indonesian cobalt. And actually, as an aside, the IEA had their Global Critical Mineral Outlook report launched yesterday. One thing that really stood out to me is that Indonesian cobalt will continue to grow such that the DRC share will actually perhaps reduce by 2040 to 50% of global production. So that's the IEA's view on things. But then with this increase in supply, we also see an increase in emissions, some 7.6 megatons in a do-nothing scenario. So the world around us is changing in the do-nothing scenario. We're seeing scope 2 emissions perhaps decreasing, but we're continuing to see this increase, firstly just because there's more material, but also there's elements such as grade erosion that we're expecting over time and that was accounted for in this analysis. And then we went through a technological analysis of abatement opportunities and started to model this 80% reduction by 2050, which would see industry emissions reduced down to some 1.3 megatons CO2 equivalent. So quite a significant reduction. Now, this is obviously predominantly to meet battery demand, and we're talking about cobalt in batteries in the context of the energy transition and decarbonising transportation and so on. So what does that actually mean? And on the right-hand side, we're looking at avoided emissions, and this is where cobalt-containing technologies are displacing predominantly in internal combustion engine vehicle use. And we see the potential for these technologies to abate and avoid some 3.5 gigatons of CO2 for these technologies. But I think there's some important context here. You know, the industry emissions are very small and play a part in this avoided emissions, but this is no reason for inaction. And I think my next slide sort of really highlights the issue at hand here. And I'm taking a sidebar and another report that we produced recently, and this was in conjunction with Minviro. We did an in-use EV LCA, and as part of that, we looked at the cradle-to-gate of battery manufacturing. And we had low-impact base case and high-impact scenarios for energy use and material sourcing. And I think what's really striking here is just the spread of impacts from low impact to high impact materials. So really highlighting the importance of good material sourcing and decarbonising our critical raw materials. And I've highlighted some figures elsewhere in the report. The cathode active material, where the cobalt and nickel appears, you know, the nickel plays a significant part in that, and cobalt does as well. So the carbon footprint does make an impact, and the OEMs will be looking at this when they're trying to meet regulatory requirements for carbon ceilings on batteries and so on. So another interesting report that you can access online on our website. But back to the main report. Here we start to sort of model out the abatement opportunities, and we see scope 3 emissions, like I say, predominate. Following that, heat decarbonisation. I know Rohan mentioned that earlier as well, and there's a good opportunity for decarbonisation there. Limestone is used extensively. That was also mentioned earlier today, and I think that'll come up later in one of my slides as well, where there's a need to decarbonise there. I think what's perhaps important, and what I don't mention on this slide, is that perhaps only 20% of the abatement technologies are both mature enough and scalable today. So there actually needs to be quite a lot of investment in these abatement technologies for them to become a reality and to be able to be applied by 2050. So there's a lot of investment that will be required, something we touch on the report. The residuals from chemicals and consumables, and one of the main residuals is sulfuric acid, which of course is very important for the high pressure acid leaching process. It's generally sourced from refining, from fossil fuels, and I'll touch on that in another slide ahead as well. So we map out we map out these abatement opportunities, and then we get onto some marginal abatement cost curves, and here we're listing out these are constrained. So by that I mean we've taken the most likely technologies, so there's no overlapping technologies, and tried to create the best opportunity to decarbonise. And here we're looking at 2050 at a global industry view. And I think what's really striking here is that at least 30% of the abatement is net present value positive, and by that I mean the earnings would be greater than discount rate. So, real savings to be made on some of them. Think about energy efficiency and use of renewable electricity in particular. But you know, 2/3 of the abatement would be below $100 per ton CO2 carbon price as well. But in remaining time, I just want to touch on a couple of points around Indonesia. So firstly, we have a MAC for Indonesia here for 2030 here. As we can see, mining has sort of minimal areas of decarbonisation, and the main impact is primary processing and refining. So the limonite part of lateritic deposits is quite shallow, so quite easy to extract. But here we see, and because for cobalt we're focusing on HPAL, we see a lot of limestone that needs to be addressed, and we're talking about scope 1 emissions, so process emissions, and this is through the neutralization of sulfuric acid using limestone. So looking at process carbon capture, alternatives to limestone as well, to really reduce those scope 1 emissions. But also looking at the actual impact of producing chemicals as well, scope 3 emissions. We have a number of country spotlights, and again, staying on Indonesia, biofuels was another focus we wanted to look on, and it's going to be an important part of decarbonisation. But it's important, you know, we're looking at hydro-treated vegetable oils here. If done properly, this can be a way to decarbonise, but if care isn't taken, there's the potential to actually have a higher carbon footprint than the petroleum diesel you're trying to displace. In particular, we're thinking about land use change, so moving from native vegetation to an oil crop, and that has the potential for significant carbon footprint, but also fugitive emissions of methane during processing, again, can have a very significant impact. So we have a brief case study here, just highlighting the challenges and the attention to detail that needs to be paid to ensure that this doesn't have unintended consequences. And then I mentioned sulfuric acid as well, and I think sulfuric acid probably one of the sort of vulnerabilities or potential bottlenecks for HPAL and its availability and its cost. It mostly comes from oil and gas at the moment as a byproduct. And what we see is fossil fuels being used to extract sulfur as a waste product. So these are Scope 1 emissions, which are unlikely to change from natural gas because of its abundance in the environment where they're removing the sulfur. And then there's processing to sulfuric acid as well. At the moment, we're often seeing the carbon being allocated to the sulfuric acid, which I think philosophically is worth challenging because that sulfur is a waste product until we convert it to sulfuric acid. And again, a case study in the report that might be of interest. And I think Eggy touched on this in more detail, so I won't dwell on this, but we see a great potential for decarbonisation in the Indonesian grid. At the mine sites, a great opportunity for increase in these, in particular of hydro, to reduce the carbon intensity and of the electricity used in mining. And finally, I just want to end on this piece about just transition. And it's really a crucial part of decarbonising. And by just transition, we mean decarbonising the global economy in a way that is as fair and inclusive as possible to everyone concerned. So it's recognising that the abatement actions that we've discussed may actually have their own environmental and human rights impacts as well. So it started out as a sort of a footnote in the Paris Agreement, and now COP30, the third iteration of the NDCs, are going to start to consider just transition. And we see it being considered in sort of legislative instruments and also financial instruments as well going forward. And the report really shows the value of considering just transition. It's important for companies in the cobalt value chain to deliver their processes with recognition of the actual and potential human rights impacts on affected stakeholders arising from the abatement measures. And so here we've identified 3 key stakeholders. I think in the case of just transition, we're often thinking about workers, but the case of, fossil fuel workers going to new jobs, but actually thinking about those working on the mine sites and the refining sites for these critical minerals. We're also thinking about affected communities around these sites, but also consumers as well, making sure that the materials we're using are actually accessible to consumers and people aren't excluded from the energy transition. So trying to think about how companies can take a rights respecting approach. And the key message of the report is that robust human rights due diligence aligned with international frameworks such as the UN Guiding Principles is key to ensuring a just decarbonisation process, and this should extend to the abatement activities as well. And we set out a framework in the report to highlight this. Very briefly, because I realise I'm 30 seconds over time, but you can think of examples such as land use for solar projects as well, and there might be competition for land use with local communities, or if you're looking at changing a chemical on site to a lower carbon one, and the disposal practices are different but aren't properly incorporated into training, into occupational health and safety training. You might have improper disposal that could then pollute a waterway and damage crops or biodiversity in the area, affecting, say, local farmers. So, try to think broadly about the activities you have and how that might affect affected communities. But again, the report has a lot more detail here. And really, to finish up, we have a lot of materials on the Cobalt Institute website, so please do visit that. And I think with that, I'll end there. Thank you, Mark.
Yeah, thank you, Tom. I think it was very reassuring to see that your presentation, as well as the conclusions drawn by Eggy, are very much aligned which is not a surprise, I think. Good. Then I will do one presentation at the very end, which is going to focus on a topic that we see emerging right now, not only in the case of nickel, but also in the case of many other metals, which relates to low carbon nickel. So first of all, can you see my slides? I hope you do. And the question is, are these discussions on low carbon nickel or low carbon metal in principle a meaningful and target leading debate or not? So first of all, where do we see these discussions on green or low carbon nickel popping up? So we see that trade platforms, and I will give one example, are looking into it. We know that the automotive industry has an interest in low carbon metals in general. Also, the stainless steel industry, with their responsible steel initiative, is looking into the topic. Regulators such as the European Commission, but also the investor community. And when we look into the drivers, then apparently it is about promoting the best performing producer. We will discuss one question that came up, which is what is the lowest and the highest nickel carbon footprint observed in our data. Ensure that decarbonisation targets are met, allow access to sustainable finance. So we know that there's the so-called taxonomy program, as an example, ongoing, not only in the European, but also in other jurisdictions, such as, for example, Brazil. And last but not least, also restrictions that might apply to market access and certain applications if you are actually exceeding a certain carbon footprint. Now, the concept, and I've taken here right now an example from our colleagues from the aluminium industry, is that that you have the same process which is applied on a global scale, that you have a consistent material input. So in the case of aluminium, it would be bauxite, that there are nearly no byproducts occurring, and that you have as a final product one major product resulting from the process. In the case of aluminium, it would be aluminium metal. And there we can follow to a certain extent the logic that the aim is to, as you can benchmark all these processes applied across the globe against each other to promote the lowest footprint, to define a threshold that have to be achieved by companies that might not be as efficient as producers elsewhere, and that you ensure that those with a low footprint have a preferred access to markets, to capital, and to permits. And that brings me to the next point. So this discussion on low carbon nickel is often linked to the strategic objectives that companies also have, like access to markets, like access to finances, and license to operate. So it is a discussion that from a company perspective needs to be followed, as otherwise you're not going to meet your strategic objectives that you defined. Now, when we look into the discussion from a nickel perspective, you can see here on the left side the requirements that need to be met. So as I said, you should have a similar or the same raw materials input, the same production process. Ideally, you have the same byproducts, that you have the same processing conditions that companies cannot influence, as well as the same products being delivered to the markets. Now, the reality check shows that in the nickel industry, we are working with very different raw material inputs. So Eki mentioned it in his presentation, was also addressed in the presentation of Rowan. We are talking about lateritic and sulfidic ores that are actually processed. Within the lateritic ores, we also see a subdivision into different mineralogies. We know that the processes are tailored to the different ores and mineralogies, so they cannot be interchanged with each other. Then we have some of these ores with a wide range of byproducts. In the case of sulfidic ores, we talk about 5, 6, 7 metallic byproducts that occur. In the case of lateritic ores, it might be one, namely cobalt. So it's a number of parameters where we see this does not match with the nickel industry, as it is a very diverse industry. And this is also shown in this flow chart that we adapted from a presentation done by the German Geological Survey, where you can see that the nickel production is actually rather complex. We are talking about different inputs. We are talking about different process routes and different outputs that are actually entering the market, depending on whether you deliver your nickel products to stainless steel production, for example. It's ferronickel, NPI, utility nickel, nickel metal that can serve the market. For batteries, it's predominantly nickel sulfate. So it's a very complex flow chart that we observe in the nickel industry globally. Now, how do these benchmarks look like? And I've taken here 3 examples. One is from Fast Markets. They actually communicate that everything that has a carbon footprint lower than 18 tons of CO2 per ton of class 1 nickel would fall into this category. And you can see that they are only looking into so-called Scope 1 and Scope 2 emissions. Now, in the case of the London Metal Exchange, a value of 20 tons is suggested, where our guidance, the Nickel Institute greenhouse gas guidance, is used as reference point to conduct the calculations. We include Scope 3 upstream emissions, and then we have also the European Commission in their taxonomy draft for nickel smelting and refining, where you can see that they are defining concrete values when it comes to the electricity being used, the fossil fuels and reagents and their carbon footprint. But they also mentioned that a decarbonization roadmap needs to be in place. And I think that this already shows that it is very complex to derive a value for low carbon nickel, as the nickel industry is so diverse. Now, our position is, first of all, when you go on our website, you will find from our member companies a wide range of different examples how nickel producers are actually working on decarbonizing their processes. We have to acknowledge that there are many parameters that are influencing the carbon footprint that are out of the control of the nickel producer. The nickel production is characterized by its heterogeneous inputs, the processes, which are also very heterogeneous, the variation in byproducts, the varying settings when it comes to the location, but also the products that are entering the market. And strictly speaking, when we look at things from a more academic or scientific perspective, such a benchmarking approach would make sense if you can identify and group producers together that have the same production process, are processing the same ore, have the same byproducts, and produce the same raw material outputs. And that is simply not feasible. So our position is, it is important, and I think what we have seen today is very promising, that companies need to start measuring their carbon footprint according to agreed guidelines, like the ones of the Nickel Institute. And this is what you have seen, I think, in all the presentations, that measuring the carbon footprint allows you to identify hotspots in your production process, that companies have to seek for ways on how to address these hotspots. That was actually shown in the both presentations of Eggy as well as of Tom, and then determine a decarbonization roadmap that is defining a company-specific strategy on how the company is going to address these hotspots and is going to achieve in a mid or long term a decarbonization. I will leave it here, and I will stop sharing my slides. I would appreciate if all the speakers could switch on their cameras, as we are right now going into the Q&A session. And I promised to those that post questions that some of the questions will be discussed right now in the Q&A session. So starting off, I would like to share a question which relates to the fact that in the data, Pablo, that we collected, we don't have a lot of production from Indonesia. So the question is, 60% from nickel comes from Indonesia, so nickel mine production comes from Indonesia, but the study that we conducted has only a fraction of companies from Indonesia in scope. So the question is whether these data that we published are representative for the global nickel industry. Pablo.
Yes, thank you for the question. No, so results are indeed cannot be considered as representative of the Indonesian production as a whole. As you rightly indicated, we only have one site that is represented within our membership in Indonesia. And currently there is a relatively high share of the market, of the nickel market in Indonesia and also in China, for which we do not have access to hard company data. And this is, of course, one of the things that our study has as an advantage. We are working with primary data that is compiled from within our member companies. And so we are limited in what we can outreach in that extent. So yeah, this is also explaining why our next steps would be to try to extend our study and to cover the remaining market that is not within our membership.
Yeah, thank you, Pablo. Now a question to you and Rohin. So looking into the figures, Rohin, that you showed and looking into the figures that Pablo shared, there's a certain variation that can be seen. Now the question is, how comes? Can one of you explain, or can you both explain why you feel that there's such a differentiation in the results between those data that you published in the report, Rohin, as well as the data that we published in our report? Pablo. So not quite sure who of you both wants to go first.
I can maybe give it a start and then you can add up, Rohin, if that's
Sounds
okay.
good.
Yeah, well, what I can say is, of course, we are trying to follow the agreed standards at an international level. So it all starts by, of course, the more generic standards at the ISO level, the GHG protocol, and those are, defining certain general rules that you need to follow when you do an LCA. But there are, of course, also more sector-specific guidelines that have been developed at the metals level, but also we have at the Nickel Institute developed guidelines on what the industry is doing at the global level and specifying the rules on how to do a calculation to ensure that the results can be compared between our members and also that can be benchmarked and establish certain trends through time. But I think one of the main differences is that we have access to a lot of primary data from our companies and that we don't have the same coverage when it comes to geographical coverage and technological coverage, as we are working primarily with our members, and so we are limited to the operations that they do.
Totally. I would like to add to that. I think actually, if you consider the results that were represented by Pablo at the Nickel Institute study and the results I presented, for example, the Nickel Institute study has really good coverage of the sulfidic or sulfide deposits, and actually our sulfide climate change impacts do match or are very much in a similar ballpark to that of the Nickel Institute's report for mining and smelting. But where we vary for sure is further on smelting, and crystallization. And I think, yeah, because we are sort of the data that we use in that report was a bit more representative or had a bit of a wider coverage. That's where you might see the variation in results. But I actually think methodologically we're very closely aligned. Pablo, Mark, and I, and Tom, for that matter, as well as the reviewers of the Nickel Institute's report, Lyle, we're all very well aligned on using the same methodology. So I actually don't think there is that much variation in the results if we'd done everything on the same basis. And I would also like to say that there was a comment on maybe it's about like modeling versus hard data. I think that's not the case. It's a bit more nuanced than that, where we have all done modeling. We are all trying to represent real world systems as ones and zeros to understand their climate change impact. However, the data that we feed into those models, that explains some of the variation. So yeah, you can see more of the granularity in the full report, both the respective full reports.
Yeah, thank you both. And I think, Rowan, just to follow up, the future is that companies will have to provide hard data. So while in the past we were working with so-called, often enough, with estimates when it comes to the inventory data, the reality is that in future, as we have to work with audited data, for example, for the batteries regulation, companies need to provide hard data. And that will also ensure that the work that also we are doing is getting better and better and more precise. Now, the next question is to Egy, and that is actually a question: is the Indonesian government behind this decarbonization roadmap? And what do you see are the main barriers to put the decarbonization roadmap in place? So what needs to be tackled in the coming years to ensure that we can see a decarbonization in the Indonesian nickel industry?
Yeah, thank you, Mark. So yes, the Indonesian government is behind the development of this decarbonization plan. So we are working with the Ministry of Planning, but we also working with other government institutions to develop this. And because again, this roadmap is not intended for one ministries, but we will put some like who is doing what across the ministries, so it will be more integrated in the context of the implementations. The barriers of to implement these decarbonization roadmap is actually we highlight several barriers. First is related with the supply of the green energy, because again, as I mentioned, the locations is far from the smelters, nickels. The sustainable materials is not really available to fulfill all the needs, the gaps. The other things is currently we are still facing limited infrastructure in terms of the connections, transmissions line, and so on. So it creates an issues on how we can replace the existing captive coal power plants to renewables. Now we also see the nickel price is like quite volatile. This also creates some financial barriers to increase the investment to low carbon nickel, because again, the companies will see the high margin, but transitions to a low carbon will definitely increase investment for this. And then the last one is the absence of the environmental and technical safeguards for nickel companies in Indonesia. So yeah, we hopefully this will be addressed in the next coming years by developing the standards for nickel industries.
Yeah, thank you, Egy. Now, next question goes to Tom. Tom, there was you mentioned in your presentation the growing supply from recycled cobalt that is going to increase in relevance in the years to come. And it's an interesting question that applies, I think, to all of the metals, namely, can these recycled materials be utilized for the products in the growth industries such as car manufacture, robotics, energy production, or does it require pure or new materials? So it's a question related to, is recycled cobalt, of different quality than primary cobalt?
Yeah, great question. I think for metals generally, it's something we address quite frequently because unlike plastics, where you have in recycling, you have chain scission and degradation of the material, metals essentially, other than say processing losses, can be recycled infinitely and can be refined to the purity level that's required for battery uses, which of course are very exacting. So absolutely, we're not talking about downcycling. We're talking about, and in the case of cobalt, in the long term, it's going to overwhelmingly be end-of-life electric vehicle batteries, where you are going to be able to recover the cobalt from, reproduce a sulfate that then can be crystallized and produced into a pCAM, and then go back into batteries again and again. So we see this as a real opportunity and a real win for circularity, vital for electric vehicles and electrification to have this sustainable process. But also, I think crucially, with metals such as cobalt, nickel, and to a less extent lithium, these are economically valuable materials where it's viable to have the recycling process and cover the costs of that processing with the value of the recovered materials.
Yeah, thank you, Tom. Question: LFP recycling. Do you see that working as well as on the NMC/NCA side?
I mean, it's not my sort of area of expertise, but I would say the challenges we see are around the value of the recovered materials. So we see many recyclers now able to recover, for instance, iron phosphate, but you have processing costs and energy costs that are required to actually do this. So I think this might be a negative externality that hasn't been quite considered around recycling of LFP. I think it can be done. It's just who's going to pay for it.
Yes, yeah. This is also very much in line with our observations that LFP recycling is currently economically not viable. It is technically possible, economically it's not viable. Now, there was a question related to recycling in Indonesia, whether we see recycling becoming relevant in Indonesia. Maybe I can start off with our observations or my observations. So we see a growing downstream industry in Indonesia. We know that the first car manufacturers are setting up plants also for EV batteries. And knowing that the production of EV batteries comes with a lot of production scrap, this is a topic that is becoming relevant rather soon also in Indonesia. And I think, Rowan, you mentioned the lifetime of batteries, that when we talk about the big amount of spent batteries, they only are going to be available depending on the lifetime of the batteries in 8, 10, 12. We are calculating with 14 years. So that is also something that we observe. Are there any comments from any one of you when it comes to recycling in general, or when it comes to Indonesia?
I'd like to echo Tom's point. Some of the work that Tom's point on the quality of things. Lots of the work that we've done at Enviro forecasts like the recycling availability of nickel, but just to reiterate that, yeah, like good hydrometallurgical processes can recover lots of things in NMC cathodes. So that should be a very viable source of primary nickel, but as I say, in a meaningful way in probably a decade's time.
Yeah, my last question to all the panelists is a very generic one, as there was a question raised about, I mean, many of the questions related to the fact that we are lacking in our data collections, hard data from Indonesian nickel producers. What do you think? Do you have any thoughts about, in one phrase, what needs to be done to convince Indonesian nickel producers to collect these data, to work with hard data, and maybe to work together closely with the Cobalt Institute or the Nickel Institute? Do you have any views? Maybe I can put people on the spot, looking into the faces. Who is smiling the most? Rowan, starting with you.
Yeah, look, more primary data is always better, but I think it's this might be slightly batting for the other team, but I think we do have reasonable quality of data from Indonesia at the moment in terms of like we understand ore grades well, and we understand the key reagents and the key amounts of energy required well. Like fundamentally, the stoichiometry exists. So primary data is always nice for like certainty and precision, but in terms of like ballpark figure, I think we're doing really well with what we have at the moment.
Yeah. Pablo, do you have any views?
Yes, I can say that well, we are here working very closely with industry for quite some time at the Nickel Institute and supporting our members into compiling and collecting this data. We see that currently there are a lot of incentives in doing that, both from the market, from different market actors, stakeholders being customers or investors, but also requirements at the regulation. And some companies are required to provide primary data for these initiatives and to show, where they stand. And in certain initiatives, also at regulatory level, there will be thresholds being set. So it's important for companies to start compiling and understanding what their impacts are. And this is where we can support as Nickel Institute.
Good. Then, Tom, do you have any views?
Yeah, I mean, you both yourselves and ourselves, we're increasingly engaging with Indonesian stakeholders, and I think that's an important element of gaining awareness of importance, getting awareness of the work that we're doing and how we can support industry activities as well. So we're continuing to do that, and indeed ourselves and Mark we'll be in Jakarta in about a week and a half's time. So some further engagement there. That market access piece that Pablo mentioned is incredibly important, and understanding the importance of being able to share primary data, both for your downstream user, your off-takers needs, but also for regulatory needs as well.
Yeah, thank you. So again, the last word is with you.
Yeah, so I think the role of the role of the government in terms of monitoring and evaluations for the nickel companies is important, and the law enforcement for the from the government is also needed to, because the government has already set up like several regulations that are mandatory for companies to report the data and informations, but sometimes it's still missing in the implementations and lacking in the context of the monitoring and reporting. So I think to strengthen the role of this monitoring framework is important, and also supported by the government in the context of Indonesia. The second one that I would like to increase, I like the idea on on Pablo for increasing the incentives, because when we are trying to, let's say, developing this nickel decarbonisation roadmap, we engage with companies and we say that we actually would like to help them on how they could also comply with the regulations and the standards. So there's several benefits for the companies to open the data, and we could help them in the to measures to develop some kind of strategy and recommendations on to reduce the emission. So I think that's a couple of things. So, yeah.
Many thanks. So we are right now at 12 o'clock. So we reached the end of this webinar. We received roughly 40 questions, and as said, they are going to be all answered as part of a meeting report that we will share with you after the webinar, together with the recording. There was a question about the presentations. We will check with the speakers whether they are fine to share the presentations with the participants of this webinar. With this being said, I would like to thank all the speakers for making them available, for the excellent presentations, for all staying in time, which is amazing. A special thanks to the interpreters who allowed us to have this webinar also done in Indonesia, Bahasa, and my colleague Claude, who was setting up everything. With this being said, it's 12 o'clock, 5 o'clock in Jakarta. Many thanks to all of you. Have a good day and speak to you soon. Bye-bye.
Thank you.
Thank you, everyone.
Goodbye.
Bye.